In this video, we will discuss the fundamental theorem of calculus, which gave us a different way other than the definition to evaluate a definite integral, right? Which is a better way to evaluate integral. So first part of the fundamental theorem of calculus makes connection with antiderivative. So let's give a quick example which serve as a motivation and explanation of the first part of the fundamental theorem of calculus. So let's say definition. Let's see example, actually. Let's say the example. Let's look at a function, right? A function is an easy function, f of x equal to x, right? Over the interval from 0, 1, right? So if you want to sketch the graph of this function, it's a straight line, right? And so this is the line here going up. And this is 0, and this is 1. So this is our function f of x equal to x. So fix any x in between 0, 1. You can evaluate the area of the region bounded by this line, this part of the whole region, right? So we define g of x is integration from 0 to x. And now remember our integral, the variable in integration is the dummy variable. You have an x in here, right? So you don't want to use the same variable anymore. That will cause confusion. So we use f of t dt. Introduce a new letter, but f of t is still equal to t, right? So that's an area of this shaded region, right? Between x, 0 and x, the region under f of x, the area of the region under f of x. So this is equal to integration from 0 to x, t dt, right? So, but that's a triangle. We know the area. When you have the base is x, the height is same as x, right? So this is 1/2 x squared. Right? For any x between 0 and 1, the integration from 0 to x is 1/2 x squared. Now you can see that g of x for sure is continuous and also differentiable, right? G prime of x is basically x. So you can see that g here is, this is our f of x. G here is an anti-derivative of f. So this observation here making a connection between antiderivative and integral, right? So this works for any functions. So this is a fundamental theorem of calculus, part 1, right? We have y equal to f of x, make sure it's differentiable, make sure it's integrable. So this function is continuous on the interval from a to b. We define g of x equal to integration from a to x f of t dt. So the result we observed from our example works for any other functions as long as a function is continuous, right? So let me try to sketch a picture here, right? You have a bounded domain from A to B. We are given a function y equal to f of x, function is good. And you fix any x between A and B, you define a function to be the integration from A to x, f of t dt, right? Then this new function, g here, is continuous on AB and also differentiable on the open interval AB, and also we know the derivative. This new function is actually an antiderivative of the function we are starting from. And so let's see a very short justification of why this is true, right? We don't have a strict proof, but we have a way to justify our result. So you can justification. So you have a better way to better feeling about this result, right? So g prime of x, we want to show this because differentiable is a property we're interested. So by our definition, this is as what? As h goes to 0, g of x plus h minus g of x over what? Over h, right? So this is as h goes to 0, integration from a to x plus h f of t dt minus integration from a to x f of t dt, right? So basically, you just change x to x plus h and calculate the integration up to there. Their difference is easy, right? Their difference is a green stripe there. H goes 0, integration from x to x plus h f of t dt over h, right? Because the function is continuous. When h is very small, f of t is very close to f of x, right? Because the function is is continuous, right? So this can be approximated by f of x times h over h. So this is basically equal to what's inside, right? This is equal to f of x. So this is how do we justify the fundamental theorem of calculus part 1, right? So you are given a continuous function over an interval from A to B. We fix any point x between A and B, take an integral from A to x, f of t dt. That's basically an antiderivative of this function f. So let's see an example. We are given g of x equal to integration from 3 to x e to t squared minus t dt. We want to find g prime of x, right? So you can see that this is our f of t. When you try to differentiate this function, all you need to do is replace t by x, right? So g prime of x equal to e to x squared minus x. So that's the answer for this example.